Well, we've looked at solving linear equations, and now we've taken a brief side trip to look at nonlinear equations that reduced to linear equations. Now we'll move up in degree to degree 2, and we'll look at solving quadratic equations, factoring or graphing. So, the first thing I will do is define what a quadratic equation is. That sounds like a good thing to begin with. Define a quadratic equation, and once again, let me remind you where we got the word quadratic from. It is from the past, and the quad in it refers to something like a quadrangle or a four-sided figure. Think of a rectangle if you like. And what is the area of a rectangle? It's something like feet squared or meters squared. In other words, it is a variable of degree 2, and that's what a quadratic equation is. So a quadratic equation in one variable, and we'll even call it a degree 2 equation in standard form. In standard form, of course, is very important, especially now with quadratics, is ax squared plus bx plus c equals 0. So here on the left, we have a quadratic. The degree has gone up by 1. It's gone up to 2. Of course, we want a not 0 as usual. And, of course, a, b, and c are real numbers. So we're not talking about complex numbers here. All right. There's the definition. Now, let's see where we're going to go from here. Note, just a strategy note about what we're about to do. Later, we'll look for a quadratic formula. I promised you one earlier, and I also promised that it would be more useful than a linear formula, and it will be. But right now, in this segment, we won't be looking for that here. What we're going to do here is, if we're lucky, I've said this all along, but if we're lucky, the left side of that standard form, ax squared plus bx plus c equals 0, will easily, we hope, factor. Now, factorization is something that's very nice when it happens. When it doesn't happen, which is, frankly, most of the time, it's of no use. Graphically, of course, under the graphical imagery here, we can always graph what? Well, we take the left-hand side, just as we did with linear equations. We take f of x equals ax squared plus bx plus c, and find x-intercepts. So that is exactly the same procedure we used before, except that now we're doing it with a new higher degree equation. So the principle remains the same. Let's start looking at examples. Now remember, we're not doing anything with what's called a quadratic formula yet. Solve for x, as usual here. And I'll take x squared minus 5x plus 6 equals 0. Solution, we will be lucky. And we are lucky. We can factor. And the factoring is quite easy. It's going to factor always into two binomials. If you're writing this down, this is the practice you should adopt. Two binomials equals 0. You know that the x is squared, so there'll be an x here and an x there. And then it's just a matter of finding two numbers that multiply to be 6 and whose sum is minus 5. Well, minus 2 and minus 3 do that after a little bit of thinking. Then if this product equals 0, as we've seen before, that can only happen if either one of the two factors is 0. So x minus 2 is 0 or x minus 3 is 0. Of course, that means x is equal to 2. or x is equal to 3. And so those are the numerical solutions here. We are, however, going to check, as I've said before, this is going to be more important as we go on. So we're going to check in what the original equation, x squared minus 5x plus 6 equals 0. We'll check x equals 2. Let's see. 2 squared minus 5 times 2 plus 6 equals 4 minus 10 plus 6. Well, if 4 plus 6 is 10, minus 10, of course, is 0, so that works. And then we try the other solution, or I guess I should say at this point, candidate solution. X equals 3. Substituted in, we get 3 squared minus 5 times 3 plus 6 equals 9 minus 15 plus 6. The 9 and 6 add to 15. Minus 15 equals 0, so that also works. So we are happy both solutions actually do solve this particular quadratic equation. Now let's go ahead and take a look at the graphical imagery. We'll learn more about this later. But right now, at least we can look at a picture and start getting our intuition correct. We're looking at the function x squared minus 5x plus 6. Now that was the left-hand side of the equation. The window I will use is minus 1 to 5 by minus 1 to 3. Now you're going to ask, where did I come up with this window? And that's a good question. Later on, as we learn more about quadratic equations, you'll be able to choose a window pretty effectively. Right now, it would be a matter of trial and error on your part. So I'm just writing these down so you can reproduce these if you like. But we'll talk more about the details of that later. Here is the actual equation. It crosses at 2 and at 3. These are the two numbers that we found. These are the x-intercepts, and of course they correspond to the two solutions we found earlier. So this function has this graph, and it strikes the x-axis twice, and those are the solutions. So x equal 2, x equal 3 correspond to these 2 points. All right. Well, let's look at another example. Try and build up a selection of examples in your mind. Here's another one to look at. Solve for x once again. This is x squared minus 6x equals minus 9. So right away you see that this is not starting out in the standard form. So if I'm going to work with this, the first thing I'm going to do is put it into standard form, which in this case is easy. I just move the minus 9 over to the left. So if I rewrite that, I have x squared minus 6x plus 9 equals 0. Moving the minus 9 over. So now this is in the correct standard form. Also, this left-hand side is the function f of x that I would graph if I wanted to look at the picture. Again, the factoring is easy. We see that this is x minus 3 times x minus 3. Now, this brings up something that's worthy of note. Notice that the factor is identically the same. So out of this, we get only one solution, x equals 3, because that will make either one of these 0, since they are the same. Now I'm going to leave the check to you, and I want to go on and explore what we can say about this when the quadratic equation factors into two identical factors. There's actually some terminology we need to learn here. We'll get to practice it later, but let's go ahead and introduce it now. Here, x equals 3 is what's called and there are several names for it. Sometimes it's simply called a repeated solution. Two other words that are also used are a repeated 0 or a repeated root. It will not matter which one you use. You'll probably start adopting one of them because they're more commonly used in a given situation. These are sometimes called zeros, roots, or solutions. But repeated is a bit vague, isn't it? It says that it is repeated, but it doesn't say how many times. We could have had an equation in which we had x minus 3 times x minus 3 times x minus 3. I grant you that would be a cubic, but we would have 3 repetitions. And to call x a repeated root, or a repeated 0, would not be very accurate. So I'd like to do better. All right. Someone might call this a double. Let me go ahead and call it root, although any of the other words would work. But again, that's not really a great choice. It is fine for 2, but what if we got up to 3 or 4 or 10? Then we'd have to find other words that correspond to double. Here is the best way to say it. It is a root or a zero or a solution of multiplicity. How many times it occurs? 2. It is a root of multiplicity 2. That is the best way, because now, if it's repeated any number of times, we just replace the number. So, that is the terminology that's used here. Graphically, just to go ahead and toss in a little graphical picture here, if you do graph this, you will see what happens, because a root of multiplicity 2 has a very interesting feature. Since there is only one solution, the x equal 3 solution here, the curve can only touch once. That means it cannot go below the axis, because that would cause it to touch twice. It also cannot be above the axis, because that would cause it to not touch at all. So to touch, the only way you can get one solution is if it touches the graph, the x-axis, just once. Now we're going to explore this later. Again, this is -1, 7 by -1, 5 for those that want to reproduce this picture. Again, we'll look at that a little bit later. So, on that point, I will stop here for this segment, and we'll move on in a moment. Now we've looked at linear equations, as I said, nonlinear equations that lead to linear, quadratic equations, and now before we go on and get the quadratic formula, which is sort of part 2 of quadratic equations, we need to do one thing that is a reminder for you. It's a complex reminder, and we'll introduce something called the principal square root of a negative number. Now this will take us back to complex numbers, but this is a good place to remind us of this. So let's go ahead and look at this. I have a number of points to make here. First of all, remember this symbol, of course, we've been using it all along for the real numbers. That stands for the reals. That set is contained in the complex numbers, which remember we denoted with a capital C. These are the complex numbers. All right, that's point number 1. So the complex numbers include all the real numbers and have new numbers added. Second point I want to make is that 1 is the real unit. So it's the unit for the real numbers, whereas I is the complex unit. It acts as the unit for complex or purely imaginary numbers. And how did we define it? Is defined by I squared is equal to -1. That was the definition of the letter I. And then we learned a few facts about I that I'll go ahead and sketch out here on this page. There's something that happens when you multiply powers of I. Because each time you get a square, it turns into a -1. Things simplify fairly quickly. You can start out with I, and then you can look at I squared, which is -1. And then you can look at I cubed, which is I squared times I, so that becomes -I. And then I to the 4th, which is I squared times I squared, which takes you back to -1 times -1, which is 1. And all of a sudden, you have set up all the different possibilities that can exist for powers of I. If you go to I to the 5th, that's just I times I to the 4th, so we're back to I. Likewise, I to the 6th is -1. I to the 7th is -I to the 8th is 1, and so on. So this cycles between 4 possible values. It can be I, it can be -1, it can be -I, or it can be 1, but nothing else. So I wanted to remind you of that. There is also the standard form of complex numbers, which I wanted to remind you of. The standard form in C is A plus BI. That's the way we write the complex numbers, where the A and the B are reals. So you take two real numbers, multiply one of them by I, add them, and you've got a complex number in standard form. All right. One other thing that's going to occur now, especially with quadratic equations, the complex conjugate. Remember the word conjugate? Complex conjugate of a complex number a plus bi. Now what is the conjugate of that number? It is a minus bi, and vice versa, which just means you can reverse the process. The conjugate of a minus bi is a plus bi. You simply change the sign between the a and the bi. Now that will become very important as we talk about complex numbers. So, just so we can practice with this a bit, let's look at an example. Write in standard form the following complex number, 1 plus I quantity squared. So we take 1 plus I squared, we want to write it in standard form. So the solution is quite easy. We take 1 plus I squared. Now that is a binomial squared. You may recall, let me jot that down here in the corner. This is something you should have memorized by now, that if we take x plus a quantity squared, we get x squared plus 2ax plus a squared. Now that's something that should be commonplace to you by now. Of course, in this case, that means 1 squared is 1, plus 2I plus I squared. But of course, I squared, 1 plus 2I, I squared is minus 1. 1 minus 1 leaves us with 2I. And if we want to be completely pedantic about writing this in standard form, we'd write 0 plus 2I. And there we are. That's the A equals 0 and the B equals 2. So there we go ahead and written this in standard form, and we've answered the question. So that's just a little bit of practice with a complex number. Now let me define something that we did not define before, but we can do now that we have complex numbers, and which is going to occur with quadratic equations. Definition. If you have a number, say big N, and it is greater than 0, which means it's positive, then we define the following. The principal square root of minus n, which is definitely a negative number, since n is positive, is, here it is, the square root of minus n, same symbol. It is by definition defined to be the square root of n times I. Now we needed a definition like this because you cannot take the square root of negative numbers in the real numbers. It is defined now in the complex numbers to be the square root of the positive part times I. So as expected, this gives us the right kind of answer when we square it. If we take minus n square root and square it, now by definition that was square root of n times I, we square that, we get square root of n squared times I squared. Now square root of n is positive, so square root of n squared is just n. So this equals n times a minus 1, and of course that's minus n, which is what we would hope would happen when we take the square root of something. We hope that when we square it, we get what's underneath, and in fact we do. So that's the new definition here, the principal square root. Let me show you a couple of examples so that we can practice this. This will be very important for our concepts involving quadratic equations. Here's a simple example just to start. The square root of minus 4. What's that? How would I write that more simply? Well, it's almost as simple as you can get, but if you want to write it in terms of the definition, this is the square root of 4 times I. And of course, square root of 4 is 2, so this is 2I. Now that's a simple one. How about this one? Let's write this in standard form. And this will be the square root of 3 plus 4I times 4I minus 3. Now that's the complex number that I'd like to write into standard form? Well, the first thing, it seems to me, would be to multiply the underneath part. So that's exactly what I'm going to do. And I'll need a little extra space there. Now, when I do this, I'm multiplying two binomials as we've done before. So I won't have room to write my little arrows now, but you'll have to just follow in your head. 3 times 4i, of course, is 12i. 3 times minus 3 is minus 9. 4i times 4i is 16i squared. And then 4i times minus 3 is minus 12i. Well, 12i and minus 12i, thankfully, add up to 0. So we're left with the square root of minus 9. And then remember, I squared is, by definition, minus 1. So that's minus 9 minus 16. That's the square root of minus 25. By definition on the previous page, that is the square root of 25 times I. And so the answer to this is 5i. And if you like the standard form, 0 plus 5i is perhaps more correct. So in this process, we've looked at the square root of a negative number, and we've rewritten it in the correct fashion. Now be very careful when you do this. This has to be done, you have to actually make this step between square root of minus 25 and square root of 25 times I. Now there's a warning here you need to be aware of, so let me go ahead and lay that out. This is about complex numbers. It's very common. A lot of folks will do this, so it's worthwhile giving a little time to. Warning, a common error. Now in general, that is to say for any x and y in the real numbers you choose, any two numbers, the square root of x times y is not equal to the square root of x times the square root of y. It's just not true. Now this is only true because I know you know that there are some cases where it is true, but I'm claiming now a general remark. This is only true if both x and y are greater than or equal to 0. So both of the numbers up here must be either 0 or positive for you to be able to take the square root of the product and get the product of the square roots. Otherwise, it just isn't so. Just to make sure you see that that's true, let me give you a counterexample here. Counterexample. Let's start out with a nice simple number like square root of 6. And I will correctly write it out as the square root of minus 2 times minus 3. Now that's perfectly correct because 6 is equal to the minus 2 times minus 3. Now, if I make the standard student mistake, and let me just mark it with an arrow here so you're aware that that's where it happens. The standard student mistake is to rewrite this as the square root of minus 2 times the square root of minus 3. Separating these two, product of square roots is the square root of a product is the product of square roots. Now, let's see what happens when we follow our definition. Square root of negative 2 is the square root of 2 times I, by definition. The square root of negative 3 is the square root of 3 times I, by definition. Now, what is this? Well, let's see. Let's pull the square root of 2 times the square root of 3 together. And then I times I is I squared. Well, square root of 2 times square root of 3 is square root of 6, of course. That is correct, because the 2 and the 3 are both positive. I squared, of course, is minus 1, so that puts a minus out front. Now look at the string of equalities we have. It says that square root of 6 is equal to minus the square root of 6. Of course, that's nonsense. If these were all correct operations here, and the first one was correct, of course, this is the operation that is incorrect. And that is exactly what I warned you about on the previous page. The square root of two numbers that are not 0 or positive, in this case both negative, is not equal to the product of their square roots. It just isn't so. So, be careful. All right. Well, now that we've reviewed complex numbers, it's time to get back to quadratic equations, and that's what we'll do next. Now it's time to look at quadratic equations from yet another point of view. And this one is where finally we can derive the quadratic formula. And we'll talk about something also called the discriminant. And of course we'll look at what graphing can tell us about solving quadratic equations. So let's go to the pad here. And first of all, before we do anything in general, we're going to work this by looking at a special case first. Now the special case, here's the question, and then we'll answer it by finding a solution by doing a derivation. How do we solve? Okay, we're solving equations here. How do we solve the simple quadratic equation? And quadratic, remember, is degree 2. Let's keep that in mind. Simple degree 2 equation. X squared equals p, where, I need to tell you what p is, where p is some real number, a constant. So this is a really simple quadratic equation. We have an x squared term, we have no x term. So let me even write that down. There's no x term. So this is a really simple case. Now one thing I want you to do is always, when you look at problems like this, look at the format. Here what we really have is box squared equals p. Okay, where p is some constant. Now keep that in mind as we go through. All right, how do we solve this? Well, let me do a derivation for this special case. For this special case, I'll do this derivation and we'll come up with the solutions. Here it goes. X squared is equal to p. Let's rewrite that with everything on the left. X squared minus p is 0. Now that's that f of x equals 0 form we've talked about. This can be rewritten as x squared minus the square root of p squared equals 0, because I can interpret any number as its square root squared. Now that's a difference of two squares. So this is a difference of squares, which is something we've used before, and it occurred in basics. This means we can rewrite this as x minus the square root of p times x plus the square root of p equals 0. Now, of course, that leads us to two solutions. X minus square root of p equals 0 gives us x equals square root of p. Or the other solution being x plus square root of p equals 0. X equals minus square root of p in that case. So with these two, we have solved this original quadratic equation. So let me put this all together on one page. Thus, x squared equals p, where p is a real number, has solutions, which we are now calling, you remember, roots or zeros. All of these words are used. X equals plus or minus the square root of p. So that is what results from the derivation on the previous page. The x squared equal p has solutions x equal plus or minus the square root of p. Now, there are a couple things I want to mention here since we're here. This is the plus or minus notation. That is simply a shorthand way of saying x is equal to plus square root of p or x is equal to minus square root of p. This just makes it shorter. Where there is another statement we can make here, just for the record, where if p is negative, then square root of p is defined, as it was on the previous segment, means, by definition, the principal square root. The principal square root of p. So that is defined, this square root symbol is defined whether p is positive or negative. And to make it even clearer, let me put it in that box form. What we now have is that if box squared equals p, that is equivalent to, or that is true if box equals plus or minus the square root of p. Now that is a fact we're going to use over and over again. So it's worthwhile sort of seeing it in that schematic form. Here are a couple of examples. Solve for x. If you're given x squared equals 5 by this result, the answer is immediately plus or minus square root of 5. No mystery, we now have the result immediately. We also have the result in the case of this example. Solve for x. If x squared is equal to minus 9, by the result, x is equal to plus or minus the square root of minus 9. And then we use the definition. This is plus or minus the square root of 9 times I. So this is plus or minus 3i. There are the two solutions in that case, which are complex numbers. Okay, with those two in mind, here's an example for you to try. Solve for x in this. X minus 2 quantity squared equals 16. And use that result that we just used. I'll come back in a moment. Let's see now how this works out. Solution. Well, before I do anything, the first thing I want to note, and this is the kind of thing you should be looking for, is that this looks like a thing squared equals a constant. Now, if you recall, we had a result that said if you had box squared equals p, then that means that box is plus or minus the square root of p. Of course, with that in mind, I can now rewrite this using exactly that form as x minus 2 equals plus or minus the square root of 16. Well, that means that x minus 2 is equal to plus or minus 4, because 4 is the square root of 16. And then this breaks into two equations, because we have plus or minus here. We'll have x minus 2 is equal to 4, so x is equal to 6. That's easy from there. And on the other hand, or, we have x minus 2 equals minus 4. And then the minus 2 goes over, and so this becomes x equals minus 2. So we have x equals 6 or x equals minus 2, and I will leave the check to you. This is not something that I'm going to do. So I hope that problem worked out for you. And now what we're going to do is we're going to move beyond this example of a simple quadratic where we have x squared equal p, where we have just a constant there, to a quadratic that is of the full general form, and try to develop what's called the quadratic formula for it. So this will be a general case, as opposed to the specific special case we looked at before, that x squared equal p case. We're going to go ahead and look at the general case and do a derivation that will lead us to a solution that will always work. Okay, and that applies then to ax squared plus bx plus c equals 0, the standard form of the quadratic equation. And of course, remember, that means that a is not 0, otherwise we don't have a quadratic, and that the numbers a, b, and c, the coefficients, are real numbers as opposed to complex numbers. Now, for convenience, and this is something we'll do later also, so it's worthwhile mentioning here. For convenience, we'll divide by a. Now, a is not 0, so we can divide by a. And that will make this leading coefficient of the new quadratic into 1, because we'll divide the a out. So in doing that, we get then x squared, we divided the a out, plus b over a, we don't know what b is, so we can only write b over a, plus likewise c over a equals 0. So now we have this in the form where the leading coefficient is 1. And we'll do this many times in the future. It makes things easier, so we don't have to worry about working with a coefficient that's not 1 here, which can cause difficulties. So what are we going to do with this now? Well, the only way we know how to solve this is to then complete the square, because we want to get this back in that special form which we had earlier. So that's what we're going to do. We're going to complete the square. Now that's something we covered in basics, so you should remember that. We practiced it a little bit between then and now. So what am I going to do? First of all, I'm going to write down x squared plus b over ax. Now that is the quadratic perfect square that I'd like to complete. I don't know what goes here yet. Equals, and on the other side I'll put minus c over a. So I've taken the c over a that was here and moved it to the other side. Now what does the rule say for completing the square? Well, in here you're supposed to add, you take 1/2 of this coefficient, so that's 1/2 b over a, and you square it and add it in there. Now, if you change one side of an equation, you have to change the other side, otherwise you've altered the equation. This side we've added this, there's no coefficient out front, so this is just exactly what we've added, there's nothing multiplied by it. So we have to now add the same thing on this side, 1/2 b over a quantity squared. And this goes in here and gets added. All right, well, by design, I'll even write that in. By design, we have completed the square on this side, so this is, of course, then a perfect square. X plus, and instead of 1/2 b over a, I'll write that as b over 2a, quantity squared. What's on the other side? Well, whatever's there. I have minus c over a, and I have plus, now let me go ahead and multiply this out. I have b over 2a, and I will then square the top and get b squared, and 2a on the bottom squared gives me 4a squared. And I might just make a little side note here, since we're here to remind you. Look what this looks like. This is a horizontal shift. Remember those? A horizontal shift by the amount 2b over 2a. So that's a horizontal shift. I just wanted you to recognize that that's what you have in front of you. Okay, well, we want to simplify this further, and that's going to be a matter of combining the right-hand side. Well, to do that, and I'll do that on the next page, I need to have the same denominator, so I will go ahead and multiply c over a by 4a over 4a. Now, that's 1, it doesn't change anything, but now the bottom is 4a squared, which is what I need on the next page. So I will go to that, and let me rewrite the left-hand side. So I have x plus b over 2a quantity squared is equal now to minus 4ac, multiplying that 4a through on the top, and the bottom is 4a squared plus b squared over 4a squared. And of course, we can now combine this into a single fraction with the denominator 4a squared. And I'll reverse the order of the top because I want my minus to come second. So I'll put b squared here and then minus 4ac. That just makes it neater. All right. Well, before I go any further, let me recognize once again the form that I had. I said I would get to this. The form is box squared equal a constant. And so the result is box equals plus or minus the square root of a constant, of that constant. Now that is that special form which we had as x squared equals p previously. All right, so with that in mind, this is the object squared equal this constant. This then becomes x plus b over 2a, that's the box, equals plus or minus the square root of the constant. The constant was b squared minus 4ac over 4a squared. Okay? Now we want to simplify this even further, of course. So I'll take one step here and then continue on the next page. A square root of a quotient is the quotient of the square roots. That means I can split the square root into the top and the bottom. So I'll make this plus or minus the square root of the top, b squared minus 4ac over, and what's the square root of 4a squared? Well, it's 2a. So, with that in mind, I can move to the next page and continue. I'm almost finished with this derivation now. Now, let me remind you what we had on the page just a moment ago. X plus b over 2a is equal to this object. I'm going to move the b over 2a to the other side and then try to combine this. So I'll have x left alone on the left and minus b over 2a on the right, plus or minus the square root of b squared minus 4ac over 2a, all of this on the right-hand side. Now these are fractions over the same denominator, so I'm almost there. And just for the sake of being able to box it, I'll put the x again. And so now I have minus b plus or minus the square root of b squared minus 4ac all over 2 times a. This is, in fact, let me be very clear, this is 2 solutions. Okay? Because there is a plus or minus here, with the plus you get 1 solution, with the minus you get another solution. So there are, in fact, 2 solutions here. And you might schematically write them as x equals minus b plus square root of whatever's there over 2a, or x equals minus b minus square root of whatever's there over 2a. Okay? Well, now that we've done the derivation, what I want to do is put it all in the form of a theorem. That's what we do in mathematics. We've done all of the hard work now. We've done the proof. And now we'll put the statement in the form of a theorem that we can always refer to. Theorem. And this theorem could very well be called the quadratic formula theorem. So I'll even put that here, the quadratic formula. This is the famous quadratic formula. It is analogous to the linear formula, but this one will be very useful, as opposed to the linear formula, which was not. And it goes like this. If you have ax squared plus bx plus c equals 0, where, as usual, a is not 0, otherwise you don't have a quadratic. And, of course, a, b, and c are real numbers. We don't want to deal with complex numbers now. Then, what is the result? If you have this equation, the result is that x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. I'll put a dot out there, say. Now, what do we have here? We have this quadratic equation has these solutions or roots. You might say 2 solutions or roots or zeros, using all the various words involved. This is the famous quadratic formula, this last box. But remember, it doesn't sit in isolation. It is a formula that's related to this equation. It gives you the solutions of this equation. You should remember these as a pair. Secondly, you should memorize this verbally also. You should be able to recite it. Minus b plus or minus the square root of b squared minus 4ac all over 2a. You should have that phrase in your mind, and that will help you remember this. And now, from here, we will make some other observations. This gives us the solution to the quadratic equation, but there's some other information here that's quite interesting. In particular, this number that's under the square root has bearing on telling you something about the solutions. So I'll set this aside and come back to it. Let me now first define that number I just mentioned. The number, it's a number now, b squared minus 4ac is called, it's given a special name, it's called the discriminant. The discriminant of the quadratic equation it's associated with, ax squared plus bx plus c equals 0. See, the a, b, and c are not just letters that float in space. They are letters that are linked to the quadratic equation. They are these coefficients in this order. Now, this number is called a discriminant. Why is it called a discriminant? Well, it's called that because it's going to allow us to discriminate between various kinds of solutions. That's its great advantage. So, algebraically, the discriminant is going to show us the following. Algebraically, what does the discriminant show us? Well, the first thing to note is, I'll write it out as an if-then form. If b squared minus 4ac, that number, is greater than 0, or if b squared minus 4ac, that number, is less than 0, in either case, now we're avoiding the 0 case, we'll get to that in a moment. If it's either greater or less than 0, then Well, before I write it down, the basic idea is, back here with the quadratic formula, is that there is a non-zero number under the square root, which means something, non-zero, will follow the plus or minus sign, which will give you two distinct roots. And that's what we conclude. Then, the quadratic equation, which is ax squared plus bx plus c equals 0, has two distinct roots, or if you like, zeros. Okay? So you're guaranteed to have two distinct roots or zeros if these are either positive or negative. Now we're going to refine this a little bit further, but that's what we have at the moment. That's the first observation I wanted to make. Now, just to add to that, recall that the square root of something is defined whether that something, that box, is greater than 0 or that box is less than 0. See, we defined in that complex reminder section how to do the square root of a negative number, and this is where it's going to come into play. All right, just to continue my observations on the discriminant, if the last case we didn't look at, if b squared minus 4ac is equal to 0, that was the one case I left out, watch what happens. Then the solution, or solutions in general, but the solution in this case is minus b plus or minus the square root of 0, because that's where the b squared minus 4ac goes, over 2a. Well, because that's 0, the plus or minus has no bearing. There's nothing to plus or minus. So it's minus b over 2a. And so that's one number. So that is 1, a root, or 0. And it is a root or 0 of multiplicity 2. So multiplicity 2, sometimes, as we said earlier, called a double root. In this case, that's probably fine, but in general, you want to think of multiplicity. And the multiplicity 2 comes in because there's sort of a phantom 2 roots here. Plus or minus 0 gives you technically 2 different roots, but of course 0 and plus or minus is the same number. So it really is just one number that we have to think of as being repeated twice. All right, so that's what the discriminant tells us algebraically. If it's positive or negative, then you get 2 distinct roots. If it's 0, you get 1 root that is double root. Let me give you a tip now as you're doing these problems involving the quadratic formula and the discriminant. Tip: even though you don't need to, perhaps, check the discriminant and do this. The discriminant, of course, is b squared minus 4ac. I'll keep writing it so you'll get it remembered. You want to check it first, because it gives you information about the roots in number, and in a moment we'll see type. And also, when you do the quadratic formula later, you've already done the part that is under the square root, so your work is simpler. So you check the discriminant first to simplify the quadratic formula later. And anything you can do to simplify your work is worthwhile doing. So that's a tip I wanted to make sure you saw. All right, now what I want to do is, I want to now look at the discriminant, but I want to look at it graphically. All right, I looked at it algebraically, and we gathered some information, but now I'm going to look at it graphically. And I'm going to need a whole page to do that, so let me move over to this page to show you. And remember now, we're talking about dealing with the function f of x equals ax squared plus bx plus c. And by setting it equal to 0, it becomes a quadratic equation, and that's what the quadratic formula gives us solutions for. Well, what I will do now is say, let's break this up into the 3 cases of the discriminant. First, there is the case where b squared minus 4ac is greater than 0. And let me just mark that off. Then there's the case where b squared minus 4ac is equal to 0. And finally, there's the case where b squared minus 4ac is less than 0. What kind of pictures can you expect? Well, here are the pictures you can expect. For the greater than 0 case, we know that we get a square root of a positive number. That means we have a real number. And so there are two real solutions. That means the graphs will be one of the two types. It will look like this, touching twice. Those are the two x-intercepts, or real solutions. Or it will look like this, again touching twice. So in this case, it will be a matter of having two real roots. I'll use the word roots here. And these, of course, are x-intercepts when we interpret them graphically. All right. If b squared minus 4ac is 0, then we get no square root, because it's a square root of 0. We get then one real root, which is repeated. Now, how is that going to reflect itself in the graph? Well, you will get a picture that looks like this. It will touch once like that, or it will come up from the bottom and touch once. And in this case, you have one real root, except that this is a real root of multiplicity 2. Multiplicity 2. And that will represent a single x-intercept. Rather than plural, back here x-intercepts, there's just one intercept. Okay, so there are the two roots, the one root in either this graph or this graph. All right, what happens if the b squared minus 4ac is less than 0? Well, then you have a square root of a negative number. Now, you know from what we did a moment ago in the complex reminder that that means we have a complex number. Complex numbers do not appear in the real plane, so what kind of picture should we expect? Well, we expect this picture. It will be like this, where it does not intersect the x-axis at all, or it will look like this, where it does not intersect the x-axis. So here are two complex roots. Two complex roots. And the nice thing about these, well, we'll see something nice about them in a minute, but the important thing for us is there are no real roots. That means no x-intercepts, because x-intercepts correspond to real roots. So there you have on one page all of the information that the discriminant will tell you. Now, there is actually one more piece of information here, down here with the complex roots. There'll be a piece of information that I'm now going to derive for you. But I want you just to think about this and keep the graphical picture in mind when you look at b squared minus 4ac being greater or less than or equal to 0. That's the algebraic picture. This is the graphical picture. And see what it tells you. Now, I'm going to summarize this again in a moment, but I want to go a little further with the complex roots and gather one more piece of information. So, regarding b squared minus 4ac less than 0, that's the case where we have the complex roots, let me go ahead and do a little derivation here. Let's write, just so I can simplify things for a moment, b squared minus 4ac equal to minus n, where, of course, n is greater than 0. So all that does is say that b squared minus 4ac is definitely a negative number. And I'm representing it as negative of some positive number, which I'm calling n. Now, this will just simplify things. Then, let's see what we have. What do the solutions look like? X equal minus b plus or minus the square root now of minus n. That's the b squared minus 4ac, all over 2a. Well, by the rule we had when we looked at the complex reminder section, this by definition is minus b plus or minus the square root of n times I, all over 2a. So the square root of negative n becomes the square root of n times I. And if we break this apart further into two separate pieces, this is plus or minus on top with the same denominator. So this becomes minus b over 2a plus or minus the square root of n over 2a times I. Well, these are, or this is, a pair of complex conjugates. These are conjugate complex numbers. And if you recall, that was a plus bi form corresponding to its conjugate a minus bi. So that was the form we saw earlier when we looked at complex numbers. And these are conjugates. So the answers that you get, the solutions you get when the discriminant is less than 0 are not only two complex roots, but they are conjugates. So you have a little bit more information. Okay, that was a lot. I've pulled it all together now in one big drawing for you. So here's what I want you to look at. And you might want to construct something like this for yourself. Let me talk you through this. Here's the function ax squared plus bx plus c, a not 0, otherwise it's not a quadratic, a, b, and c real. And then I have the discriminant, b squared minus 4ac being greater, equal, or less than 0. The number of distinct roots, or zeros, of f of x equals 0. When this function is 0, that's the quadratic equation. You get 2, 1 with multiplicity 2, so you sort of have 2 anyway, and 2 here for the complex case. They are real, real, and complex, and these complex numbers are conjugates. And if you try and take this function up here and graph it as y equals f of x, when you have two real roots, that is when the discriminant is positive, you have one of these two pictures where it intersects twice. If you have equals 0, you have one real root repeated, so it touches the x-axis once, this way or this way, and it misses the x-axis entirely if they're complex. So please look at that and give it a little bit of thought. And when you work these out yourself, you might want to have your own version of this handy to function with. All right. Let me give you a note here before I move on to some problems. This is just something to remind you at this point. Remember the a, b, and c in the discriminant and the quadratic formula this is something you want to keep in mind. In the discriminant and the quadratic formula are from the standard form ax squared plus bx plus c equals 0. It is crucial that you remember that. You must have it in this form. You cannot have parts of this on the other side of the equal sign. Everything must be on the left. The coefficient of x squared is the a, the coefficient of x is the b, and the constant term, whatever it is the c. It must, the equation, the quadratic equation must be in this form before you can create the quadratic formula or use the discriminant. Now that's something that students tend to forget, and I wanted to make sure that you were clear on that. Now it's time for a problem, so let me pose one to you here. Here's the problem. Find out how many solutions and what type. Do not solve for x. I don't want you to find the solutions. I just want you to tell me how many there are and what type. Number A is 3x squared plus 4x plus 5 is 0. B is 2x squared plus 4x plus 1 equals 0. And C is 9x squared minus 6x plus 1 equals 0. So we'll pause here and give you a chance to try this, and I'll be back. Well, how did you do? Did you get them all? Let's see. Solution. Let's do A first. Well, of course, the key to this is using the discriminant. Now, luckily, all three of these are in standard form to begin with, so you just have to remember how the discriminant goes. The discriminant is b squared minus 4ac. So for the first one, that will be 4 squared minus 4 times 3 times 5. So I work that out. That's 16 minus, let's see, that's 12 times 5, that's 60. And I don't have to go any further. Oh, I know immediately 60 is bigger than 16, so this is less than 0. Now, I didn't care what this number was because I wanted to know the plus or minus sign and not the exact value. Because with the plus or minus sign being negative, that means there are two complex conjugate solutions, or if you like, roots or zeros. Okay? So don't make work harder for yourself than you need to. If you're going to do the quadratic formula later, yes, you should actually calculate this out because you'll need it. But we don't need that right now. All we need to know is that it is negative. Since it's negative, we're done. Let's look at the solution for number B. Again, I'm going to look at b squared minus 4ac. Now in b, bringing b back here, b has 2x squared plus 4x plus 1. So that's my a, b, and c. So I'll have 4 squared minus 4 times 2 times 1. That's 16 minus 8. And again, I don't need to calculate any further because I can immediately see that that's positive. That tells me I have 2 real solutions, or roots, or zeros. If I want to do the quadratic formula later, of course, I'd want to calculate 16 minus 8, but I don't need it right now. Again, the third one, b squared minus 4ac equals, let's bring that back here, that was 9x squared minus 6x plus 1. So be careful with your negative signs now. b is negative 6, so negative 6 squared minus 4 times 9 times 1. That's 36 minus 36. Well, that's a calculation I can do immediately. That's 0. And of course, that means I have one real solution, and that has multiplicity 2. So you can think of that as a repeated solution. It's a double root, or a root of multiplicity 2. Now that wasn't bad. It was important for you to realize that with the discriminant, if all you're interested in is the number and type of solutions, you just need to know whether it's positive, negative, or 0. You don't actually need to know what the number is. Okay, well, let's look at a case where you actually do need to know what the number is. Let's look at an actual quadratic equation. Here we go. Nice simple quadratic equation. Solve for x. 3x squared minus 5x plus 1 equals 0. Let's see what you can do with that. This is our first quadratic equation. So let's analyze the solution here. Solution. First, we'll look at an algebraic version of it, and then I'll show you the graphical version, so you'll have both viewpoints. Algebraically, as I recommended, this a handy thing to do is always to find the discriminant, b squared minus 4ac, immediately. Now, I don't particularly care that I'm going to end up knowing that there's 2 real or 2 complex or 1 real solution repeated, because I'm going to do the quadratic formula in a moment and find that out myself. But this will allow me to complete a calculation up here that I won't have to repeat later when it's more complicated. So b squared, let's see, I've got, that's minus 5 squared, minus 4 times 3 times 1. That's 25 minus 12. And now I'm actually going to finish this out and get 13. Now 13 is greater than 0. And if I want to pause and mentally consider, I now know that I have 2 real roots, or 2 x-intercepts. And that will be confirmed later. But I wasn't interested in that. What I really wanted to know, I'm solving for x, I want to know what the quadratic formula would give me. So the quadratic formula is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Well, we've done the part under the square root, which is the advantage of doing it that way. So this becomes, minus b will be 5, plus or minus the square root of 13. There's that 13 we just figured out. 2 times a is 3, so that's 6. So from here, I can write down the exact solutions. And if I so desire, I can simplify those, or approximate those rather. So that means x is equal to 5 plus or minus, remember, so this is plus this time, or plus square root of 13 over 6, or x is equal to 5 minus square root of 13 over 6. Now, if you want exact solutions, there they are. But in practice, those are not very enlightening. It is usually better to go ahead and do an approximation. I put this in my calculator, and you should try that. I get 1.43 truncated, or cut after the second decimal place. And in the second case here, I get 0.23. And these will be correct, as we always do, to 2 decimal places. And it is truncated, as I said. Okay, and the check will be left to you. I'll let you check that out. And I'm going to move on and look at the graphical version of this and see if I can see that these two are actually x-intercepts. I won't do graphical confirmation on all of these, but let's start off by doing one at least. Graphical confirmation. Okay, and we are dealing with the function f of x equals 3x squared minus 5x plus 1, because this was the quadratic that was set equal to 0. The window I'm looking at, for those that want to reproduce this, is minus 1, 3 by minus 2, 4. And again, later as we learn more about quadratics, you'll be able to discover these on your own without too much difficulty. For one thing, how would I discover the domain? Well, from a previous page, I see that these two are the places where the graph crosses. So if I just go a little bit above the largest and a little bit below the lowest, I know that I'm going to at least get the places where they cross, and then I can experiment from there. All right, here is the picture that I got with my calculator. You can try and verify that if you like. Here are the two axes that appear, and the graph looks something like this, where this point here is the point that we marked as about 0.23, and this one was about 1.43. And so you can verify that those are in fact the x-intercepts for the graph of this function, which looks like that. So there you have a nice picture to go with your algebraic calculations, and that's always what you want to try and do. So you can see that both of them occur. Okay, well, let's look at another example. Here we go. Example. Solve for x. X squared minus 4x plus 8 equals 0. And this one we will not pause for. I'll just go ahead and work this out because there's a point I want to make here. Solution. Again, I'm going to use my handy advice and look at the discriminant first, b squared minus 4ac. That's minus 4 squared minus 4 times 1 times 8. And if I work that out, that's 16 minus 4 times 8 is 32. And that is minus 16, which is less than 0. Of course, the minus 16 is what I'm interested in the quadratic formula. So I can go right to the quadratic formula, having done that first handy step. And so x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Well, now I substitute in. Minus b is 4, plus or minus the square root of minus 16, all over 2 times a, which is just 2. And now this is the square root of a negative number. When we looked at a complex remainder, we saw how to rewrite that. So this is 4 plus or minus now, square root of 16 times I, all over 2. So that's 4 plus or minus square root of 16, of course, is 4. 4i over 2, and then remembering how to do your division, the 2 divides into each of these, 2 plus or minus 2i. And these are the two complex solutions, and please note that these are conjugates in complex numbers. Okay, I just wanted to show you that one of these will occur like this, and I'll leave the check to you, left to you. That is, take one of these numbers, if you like, and try it back in the original equation and see if you get 0, as you should. And that'll be a nice practice for you to do with complex numbers. All right. Let me put in a technical note here, because I know you all have your calculators lying around somewhere. Technical note. Many, and probably yours, many graphing devices have an approximate, it's usually the way they work, an approximate, what you might call a quadratic equation solver. Now it'll be named different things on different calculators, which is built in. So, very often, since a quadratic equation has standard form ax squared plus bx plus c equals 0, and here's where standard form comes in and is important again, very often you can enter in your calculator, there'll be a place to enter the a, b, and c, and then the calculator will do the work of finding two approximate solutions. Now this is handy. It's only going to occur for quadratics because they're degree 2 and they're fairly small, and there's a quadratic formula after all that can be programmed into the calculator. But I wanted you to know that these things exist and can save you a little bit of trouble. Okay, let's summarize everything that we did here about quadratic equations, and then we'll stop and you'll have lots of time to practice on your own. So here's a summary. Similar to the summary that I gave for solving linear equations, this is solving quadratic equations. And there's quadratic equations, let me remind you, in one variable. And just for the record here, we'll call it x for what I'm about to do. We're solving quadratic equations in one variable. Okay? Well, I'm going to be very brief here. There's not a lot of room on this pad to list all the details, but I've worked them out now, so you have them in your notes. Briefly, the first thing you should do is get your quadratic in standard form. Now this was not crucial for linear equations, but it is crucial for quadratic if you want to use any of the results we've developed. So ax squared plus bx plus c equals 0 is the standard form. Then I recommend, as I've said, to look at the discriminant. Now depending on the problem you're working on, discriminant of course is b squared minus 4ac, that may be all you need to know. You may only want to know whether there are any real roots at all, and if so, how many. Now, I'll put in here in parentheses, because this really recalls a previous segment, factor if easy. But frankly, this is rare. In usual kinds of quadratics that occur in practice, you're not going to be able to factor them. In textbook cases you will, but in quadratics that occur in applications you probably won't. In any case, in all cases, the quadratic formula tells you what x is. X will be minus b plus or minus the square root of b squared minus 4ac all over 2a. And there's your all-purpose formula. It will always work. Even if things are easier to do another way, this will still get you the right answer. Then at the next stage, if you want, you can approximate if desired. And a lot of times the results that you get from the quadratic formula are exact but not very practically useful. So you might want to turn them into decimals. And then finally, if you really want to get a good sense of things, at least now while you're learning it, you want to confirm graphically. That's if desired. Okay. Well, those are the basic ideas behind solving quadratic equations. It's now time for you to practice them. When I come back, we'll do a number of examples for linear and quadratic equations, and then we'll do some other mathematical models also.